Without radar vectoring, an instrument procedure relies on pilot self-positioning at the initial approach fix, IAF, and then flying a published aerodrome procedure. This may be done using a facility on the aerodrome that serves both as the IAF and the MAPT. Some form of track reversal procedure is required, in which the aircraft is flown outbound from the facility on a defined track, and then turned to fly inbound back towards the facility. A simple procedure should provide for an outbound track from the fixed facility, followed by a track reversal inbound back towards the runway. This is called a procedure turn or base turn. The standard procedure for track reversal is the procedure turn and is defined as a turn from outbound to inbound in which flown tracks are reciprocals. It has two variations, which we will show you. The 45-degree or 180-degree procedure turn is the first variation and requires track guidance to a point, timed or DME, where a 45-degree turn is made, followed by a straight leg of either 1 minute for Category A or B aircraft, or 1 minute 15 seconds for Category C, D and E aircraft. At the end of the timed leg, a Rate 1 turn is made through 180 degrees to bring the aircraft into a position to intercept the reciprocal of the outbound track at an angle of 45 degrees. The 80-degree or 260-degree procedure turn requires track guidance to a point using time or DME as a reference, where an 80-degree Rate 1 turn is made, followed immediately by an opposite direction 260-degree Rate 1 turn. In still air, the procedure should take exactly 2 minutes. A published procedure turn illustrated on an approach plate would look like this. An alternative to this is the base turn procedure, which is usually associated with a VOR beacon. A base turn can be specified where the inbound track is not the reciprocal of the outbound track. The specified outbound track is followed to a predetermined point at which a Rate 1 turn is made so that the aircraft rolls out onto the required inbound track. In order to obtain an accurate outbound track, the procedure is defined to allow an aircraft to maneuver at the IAF prior to commencing an instrument procedure. You will soon discover that the racetrack pattern, which consists of a turn from the inbound track through 180 degrees at the facility or fix, after which an outbound leg is flown to a point defined by time, or at a fix at which another 180-degree turn is made, to bring the aircraft back onto the inbound track to the aerodrome. It is used where aircraft are required to enter a holding pattern prior to commencing the instrument procedure, and where the orientation of the holding pattern does not permit either a procedure turn or a base turn to be used. It will normally be specified as an alternate procedure, and specific instructions will be on the plate. Racetrack procedures are usually used where sufficient distance is not available in a straight segment to accommodate the required loss of altitude, and when entry into a reversal procedure is not practical. In these cases, the particular pattern one flies is prescribed to ensure that the aeroplane remains within the designated airspace. The pilot must strictly adhere to the directions and timings. The following specifies the procedures to be adopted when flying racetracks and reversals. Entry. Unless specified otherwise, procedures will be entered from a track within plus or minus 30 degrees of the outbound track of the reversal procedure. For base turns where the plus or minus 30 degrees direct entry sector does not include the reciprocal of the inbound track, the entry sector is expanded to include it. Speed restrictions. These may be specified, in addition to or instead of aircraft category restrictions. These speeds must not be exceeded to ensure the aeroplane stays within the designated area. Bank angle. Procedures are based upon a bank angle of 25 degrees, or the bank angle giving a rate of turn of 3 degrees per second, a Rate 1 turn, whichever is less. Descent. The aeroplane is to cross the fix or facility and fly outbound on the specified track, descending as necessary to the specified altitude. All further descents should only be made when established on the inbound track. For reasons of safety, all turns are level turns. Outbound timing racetrack procedure. When based upon a facility, the timing starts when abeam the facility, or when attaining the outbound heading, whichever is later. When based upon a fix, timing starts from attaining the outbound heading. The turn onto the inbound track should be started within the specified time adjusted for wind, or when encountering any DME distance or radial bearing specifying a limiting distance, whichever is first. Wind effect. Due allowances should be made in both headings and timings to compensate for the effects of wind to regain the inbound track as accurately and expeditiously as possible, and therefore achieve a stabilized approach. DME distances should not, however, be exceeded when flying the outbound track. RNAV procedures, based on VOR DME co-located facilities, are non-precision procedures and are increasingly being used. Aircraft equipped with approved RNAV systems may use these systems to carry out VOR DME RNAV approaches, providing that before flight it is ensured that the RNAV equipment is serviceable, the pilot has current knowledge of how to operate the equipment and achieve optimum levels of accuracy, the published VOR DME facility upon which the procedure is based is serviceable, the input data is up to date. RNAV systems are now able to project a vertical path angle, VPA, to create the so-called Approach Procedure with Vertical Guidance, APV. This effectively turns a non-precision approach into a kind of precision approach. The procedure does not meet the precision approach criteria and is a hybrid. However, it has a glide path and does replace the minimum descent altitude or height of the non-precision approach with a decision altitude or height of a precision approach. PAN-OPS suggests decision heights of 250 to 300 feet, depending on the aeroplane type, accuracy of the RNAV equipment, etc. Another term associated with this type of procedure is Baro VNAV, which is, of course, vertical navigation of the RNAV system, using the pressure altimeter. You must not forget that there are several factors that affect the accuracy of RNAV systems. To remind you, these are ground station tolerance, airborne receiving equipment tolerance, flight technical tolerance, system computational tolerance, and distance from the reference tolerance. As part of an instrument arrival procedure, a shuttle may be prescribed at the IAF, where to achieve the specific altitude at the final approach fix or final approach point would require excessive rates of descent from the minimum altitude at the end of the approach. The shuttle is therefore part of the arrival procedure of climbing or descending in a holding pattern. There are 5 standard segments of an instrument approach procedure. The following diagram illustrates these. Arrival routes are published where necessary, or where an operational advantage is obtained. The route will normally end at the IAF. Omnidirectional or sector arrivals can be provided, taking into account minimum sector altitudes. When cleared to leave the ATS route or airway, control will be transferred to the approach controller at the destination aerodrome, and the aeroplane will be cleared to the facility at a specified level. The aeroplane flies to the IAF, and with the approach plate to hand, the pilot will report. In the initial approach segment, the aeroplane has left the en route structure and is manoeuvring to enter the intermediate approach segment. The aeroplane approach, speed and configuration will depend on the distance from the aerodrome and descent required. Normal track guidance is provided along the initial approach segment to the IF, with a maximum intercept angle of 90 degrees for a precision approach and 120 degrees for a non-precision approach. If a course reversal is required, it is usually accomplished during this segment. There will be no intermediate fix as such, but the aircraft will be considered to be on an intermediate approach when it has completed the reversal manoeuvre and is inbound to the final approach fix or point. The intermediate approach segment is where the aeroplane's speed and configuration should be adjusted to prepare the aeroplane for the final approach. For this reason, the descent gradient is kept as low as possible, and the obstacle clearance requirement reduces from 984 feet to 492 feet in the primary area, reducing to 0 at the outer edges of the secondary area. The aeroplane is then flown with increasing accuracy to the FAF along the intermediate approach track. If there is no FAF, this leg is considered to be the final approach segment, and 90 metres of obstruction clearance must be guaranteed as the aircraft descends to MDA or H, which we will look at in more detail later on. For a precision approach, the intermediate approach segment will allow descent to an altitude such that the glide path can be intercepted from below. This avoids any false glide path problem. Where the intermediate approach segment intersects the glide path, it is called the final approach point, FAP, and is a point in space rather than a fix. Often, however, the outer marker will be heard around about this time. This is the segment in which alignment and descent for landing are made. A final approach may be made to any runway for a straight-in approach and landing, or to an aerodrome for a visual manoeuvre. Don't forget that two types of approach can be made: the non-precision approach and the precision approach. The non-precision approach with final approach fix has a segment that begins at a facility or fix, the FAF, and ends at the missed approach point, MAPT. The FAF is positioned on the final approach track at a distance that permits configuration and descent from the intermediate height to the MDA or H for a straight-in landing or circling. The optimum distance of the FAF from the threshold is 5 nautical miles, the maximum distance being 10 nautical miles. The FAF is crossed at or above the specified altitude and the descent initiated. A step-down fix may be incorporated, in which case 2 OCA or H values will be published. For a VOR or DME approach, several types of fixes may be depicted, each with its own crossing altitude. The non-precision approach without final approach fix exists when an aerodrome is served by just a single facility located on or near the aerodrome and has no other suitable facility designed to form an FAF. A procedure is designed where the facility is both the IAF and the MAPT. The procedure will include a minimum altitude or height for a reversal procedure or a racetrack. In the absence of an FAF, descent to MDA or H is made once the aeroplane is established inbound on the final approach track. Descent to MDA or H may be made immediately, if there is no step down. However, particularly for large aeroplanes, a continuous descent final approach, CDFA, would be preferred. The CDFA treats a non-precision approach as if vertical guidance were available. A 3-degree glide path is constructed from a point 15 metres or 50 feet above the runway threshold back to the final approach fix. This descent path is followed until a decision to abandon or continue the approach is made sufficiently above the MDA or H, so as not to jeopardise obstruction clearance should a go-around be the decision. Research has shown the non-precision approaches carry an increased risk of controlled flight into terrain, CFIT. The CDFA allows constant supervision of speed, power, configuration, descent path and height, an ideal situation for managing the final stages of approach of an airliner and thereby avoiding CFIT. Until standalone GNSS precision approaches are fully developed, a precision approach will probably mean an ILS approach, and in this instance, the final approach segment begins at the FAP. You should recall that this is the point in space on the center line of the localizer specified for the final approach track, where the intermediate approach altitude or height intersects the nominal glide path. The width of the ILS final approach area is much narrower than those of non-precision approaches, and descent must never be initiated until the aeroplane is within the tracking tolerance of the ILS localizer. The ILS Obstacle Assessment Surface, OAS, assumes that the pilot does not normally deviate from the center line by more than half-scale needle deflection after becoming established on track. In the event of loss of glide path during the final approach on an ILS precision approach, the approach will become a non-precision approach and have to use the OCA or H published for a glide path in operative circumstance. In any event, the final approach segment ends either at touchdown or at the missed approach initiation point, if a missed approach is flown. When determining the decision height for an ILS approach, the obstacles in the approach path and missed approach areas, along with the constraints of the ILS installation, are considered. The calculated OCA or H is the height of the highest approach obstacle, or equivalent missed approach obstacle, plus an aeroplane category related allowance. The OCA or H is published on the plate for the categories of aeroplane for which the approach procedure is designed. The values assume the following as standard. Cat 1 is flown with a pressure altimeter. Cat 2 is flown with a radio altimeter and flight director. Wingspan is not more than 60 meters, and the vertical distance between wheels and glide path is no more than 6 meters. Missed approach climb gradient is 2.5%, and the glide path angle is a minimum of 2.5%, has an optimum of 3%, and a maximum of 3.5%. If the necessary visual criteria for continuing the approach are not met at decision height or minimum descent height, MAPT, or at any time during the instrument approach that the pilot is unable to continue, the designated approach procedure requires the pilot to fly a missed approach immediately in order to be protected from obstacles. If a pilot decides to initiate the procedure before he reaches the MAPT, then he will be expected to fly to the MAPT point and carry out the procedure in full. The missed approach procedure is always detailed on the instrument approach plate, together with the loss of RT procedure, and it is expected that a pilot will fly the procedure as published. The missed approach is assumed to be initiated no lower than the decision height or altitude in a precision approach, or at a specified point in a non-precision procedure, not lower than minimum descent height or altitude. The MAPT in a procedure is defined as the point of intersection of the glide path with the applicable DA or H, a navigational facility, a fix, a specified distance from the FAF. When the final approach fix is defined by a navigational facility or a fix, but the missed approach point is not, then the distance from the FAF to the MAPT is published on the approach plate and is used for timing purposes to the MAPT. In all cases where timing may not be used, the procedure is annotated, timing not authorized for defining the MAPT. There are 3 phases to the missed approach procedure: initial missed approach, intermediate missed approach, final missed approach. The initial missed approach begins at the missed approach point and ends where the climb is established. The maneuver in this phase necessitates the attention of the pilot on establishing the climb and the changes in the aeroplane's configuration to prevent further descent. Guidance equipment cannot normally be fully utilised during these manoeuvres, and therefore no turns are specified during this phase. The intermediate phase begins at start of climb, and is the phase in which the climb is continued, normally straight ahead. It extends to the first point, where 50 metres obstacle clearance is obtained, and can be maintained. The climb gradient will be 2.5%, unless it says otherwise on the approach plate. The intermediate missed approach track may be changed by a maximum of 15 degrees from that of the initial track, and it is assumed that the aircraft will begin track corrections. The final phase begins at the point where 50 metres obstacle clearance is first obtained, and can be maintained. It extends to the point where a new approach, holding, or a return to en route flight is initiated. Turns may be prescribed in this phase. The turning missed approach is only prescribed where terrain or other factors make a turn necessary. Where turns greater than 15 are required, they shall not be prescribed until at least 50 metres of vertical clearance above obstacles has been ensured. If a turn from the final approach track is made, a specially constructed missed approach area is specified. The turning point is specified in one of two ways. At a designated facility or fix, the turn is made on arrival overhead the fix or facility. At a designated altitude, the turn is made upon reaching that designated altitude, unless an additional fix or distance is specified that limits early turns. Visual manoeuvring, or circling, is defined as the visual phase of flight after completing an instrument approach, which is not suitably located for a straight-in approach, to bring an aircraft into position for a landing. The visual manoeuvring area for a circling approach is determined by drawing arcs centred upon each runway threshold and joining those arcs with tangential lines. The radius of those arcs is related to aircraft category, speed, wind speed, 25 knots throughout the turn, and bank angle, 20 degrees or 3 degrees per second, or whichever requires less bank. It is possible to sectorise the visual manoeuvring area and eliminate from consideration areas where prominent obstacles occur. When this option is exercised, the published procedure will prohibit circling within the sector with obstacles in it. This diagram illustrates the situation. When the visual manoeuvring or circling area has been established, the obstacle clearance altitude or height is determined for each category of aircraft. A circling approach is a visual flight manoeuvre, and as such, each circling situation will be different because of variables such as final approach tracks, runway directions, and meteorological conditions. No single procedure could therefore be designed to cover every situation. After initial visual contact, the assumption is that the runway threshold or approach lighting aids, or other identifiable runway markings, should be kept in sight while the aircraft is at minimum descent altitude or height for circling. If visual reference is lost while circling in such circumstances, the pilot should carry out the missed approach procedure specified for that particular instrument approach procedure. The pilot should first make a climbing turn towards the landing runway and aerodrome overhead to preserve obstacle clearance. Secondly, he should complete the missed approach procedure. When additional margin is added to the obstacle clearance altitude or height, for operational considerations, a minimum descent altitude or height is specified. Descent below this limit should not be made until visual reference has been established and can be maintained, the pilot has the landing threshold in sight, the required obstacle clearance can be maintained, and the aircraft is in a position to carry out a landing. In bad weather or times of peak traffic flow, it will be most unlikely that you will be able to fly a straight-in approach to an aerodrome. Aeroplane holding procedures have been created and may be likened to temporary parking areas for aeroplanes. Obviously, aeroplanes can't stop, but they can remain in the vicinity of a radio navigation facility for as long as is required. The majority of arrivals will start from a holding pattern where the aeroplanes are stacked up, with the necessary vertical separation applied. As the bottom aeroplane departs the hold to start its approach, then the stack is shuttled down to a lower level, one at a time, to eventually start their approach. Holding is a procedure you will become very familiar with, and will form an important part of your ability to demonstrate that you can fly the aeroplane, maintaining height to the required standard, and navigating with reference to VOR and NDB navigational aids. Deviating from any in-flight holding procedure would incur the risk of excursion beyond the perimeters of established holding areas, established in accordance with PANS OPS. The shape and terminology of a holding pattern is shown here. In flying the holding pattern, all turns are to be made at an angle of 25 degrees or at a rate of 3 degrees per second, a rate 1 turn, whichever requires the lesser bank. All the procedures depict tracks that pilots will be able to maintain, making allowances for known wind by applying corrections both to heading and timings. If for any reason a pilot is unable to conform to the procedures for normal conditions, air traffic control should be informed as soon as possible. Holding patterns are to be flown at the speeds illustrated in this table. There are 3 methods of joining a holding pattern based upon the heading of the aircraft as it approaches the holding fix. These joining methods are more commonly known as entry procedures or entry sectors. Each sector has a 5-degree overlap, within which the pilot has the choice of either of the adjacent sectors. The first entry procedure to examine is the parallel entry. The parallel entry procedure is used by aircraft approaching the holding fix from a specific sector. This sector is an arc 110 degrees wide, starting from a line parallel to the inbound segment of the hold. Therefore, in the example on screen, all aircraft arriving with a heading from 090 degrees to 200 degrees will use the parallel entry procedure. The procedure follows that when the aircraft arrives overhead the fix, the pilot changes heading to parallel the inbound track of the hold. This track is maintained for 1 minute, depending on the hold, after which the pilot turns towards the hold for a rate 1 turn, so that the aircraft either goes direct to the fix or it captures the inbound segment. On reaching the fix, the pilot will fly the normal holding pattern, as shown. In fact, with the 5-degree overlap, a Sector 1 parallel join is permissible on all headings from 085 clockwise up to and including 205. The second entry procedure to examine is the offset entry. This sector is an arc 70 degrees wide, starting from a line parallel to the inbound segment of the hold, angled away from the holding side. Therefore, in the example on screen, all aircraft arriving with a heading from 090 degrees to 020 degrees will use the offset entry procedure. Upon reaching the fix, the aircraft is turned onto a heading which is 30 degrees divergent from the inbound track. This is maintained for approximately 1 minute, after which the pilot will turn to capture the hold track and return to the fix. On reaching the fix, the pilot will fly the normal holding pattern, as shown. Again, because of overlap, the Sector 2 offset join is permissible for magnetic headings of 015 clockwise through 095. The third entry procedure to examine is the direct entry procedure. This entry sector is an arc 180 degrees wide and covers the remaining area of approaches to the fix. Therefore, in the example on screen, all aircraft arriving with a heading from 200 degrees to 020 degrees will use the direct entry procedure. Upon reaching the fix, the pilot turns the aircraft to follow the normal holding pattern, rolling wings level on the outbound track of the hold. Again, and this is the most likely scenario, especially for student pilots, the Sector 3 direct join is permissible for magnetic headings of 195 clockwise through 025. This completes the 3 entry procedures to a hold. Holds do vary in their orientation, segment length, speed and direction, so be familiar with the holds at the arrivals area of your planned and alternate destinations. The still air time for flying the outbound entry heading should not exceed 1 minute if at or below 14,000 feet, or 1.5 minutes if above 14,000 feet. Where DME is available, the length of the outbound leg may be specified in terms of distance instead of time. Having entered the holding pattern on the second and subsequent arrivals over the fix, the aeroplane is turned to fly the outbound track, which will most appropriately position the aircraft onto the inbound track. Pilots must compensate for wind during this manoeuvre. So having been instructed to hold at a certain fix, on the second time around the hold, the pilot will report that he is holding at the specified height at the holding fix. When cleared to descend in the hold, the aeroplane should descend as soon as possible. There is no need to wait until over the fix. This process of descending is known as shuttling. Air traffic control will specify a time of departure from the holding pattern, and pilots should adjust their flight pattern within the limits of the established holding procedure in order to leave the holding point at the specified time. A holding pattern is cited with specific bounds and contains the basic holding area and the entry area. The basic holding area at any particular level is the airspace required at that level to encompass a holding pattern based upon allowances for the aircraft, speed, wind effect, timing errors, and holding fix characteristics. Entry to this area includes the airspace required to accommodate the specified entry procedures. A buffer area surrounds this and extends 5 nautical miles beyond the boundary of the holding area, within which the height and nature of obstacles are taken into consideration when determining the minimum usable holding level of the holding pattern associated with the holding area. The minimum permissible holding levels are illustrated here and provide appropriate clearance.